What is the temperature profile at steady state? What's the temperature profile? Quadratic, linear? Yeah? Anyone? You want to try? What's the temperature profile? Linear, right? So you will have a linear temperature profile. Okay. So supposing I say that T1 and T2 are the temperatures at the either side of the boundary. It's a 1D problem where you have heat conduction happening in this direction. Yeah, but I can still have a higher temperature. Slope is supposed to be right. So supposing if I have a symmetric condition, okay. So this is the kind of profile I'll have, right? Okay. So supposing if you have adiabatic, then what you will have is a quadratic profile, right? So it's not linear. So how many of you said linear? You should understand that when you have a flux boundary condition, this is very important to understand this. When you have a flux boundary condition, you should always make sure that the gradient at that location is 0. Okay? Very good. So supposing, so what I want to look at is what is the convective rate at the boundary, right? So convection is happening only in that location. So I want to look at what is the convective rate, and I want to know when can I lump the conduction process inside the solid. So what should I do? I need to compare the rate of conduction and the rate of convection at the boundary, right? That's what I need to do. Because these are two competing processes, I want to know when can I ignore the conduction process. So what I need to do is I need to write a energy balance at x equal to L. That's what I need to do. Okay. So minus k dt by dx at x equal to L should be equal to the amount of heat that is transported because of convection, right? So that will be T2 minus T infinity, right? That is x equal to plus L. So the flux of heat that is transported via conduction at the boundary should be equal to the amount of heat that is actually transported from the solid to the fluid that is circulating around. Does everyone understand this? Okay. So now, supposing I define a variable called z, okay, which is x by L. So now I scale the dimensions. So keep in mind that when I said when you lump it, the dimension of the system plays an important role. So when you want to compare the two rate processes, it is useful to non-dimensionalize the coordinate system. So let us now define a new variable z and set x by L is now that quantity, and so I can put that here. So it will be minus k divided by L into dt by dz at z equal to 1, that's equal to h into T2 minus T infinity. Okay. So I can do an algebraic manipulation of this. So dt by dz equal to 1 is given by h into L by k into T infinity minus T2. Okay, is that clear to everyone? So now HL by K equal to dt by dz at divided by T2 is nothing but temperature at z equal to 1. Okay. So this quantity is what is called BO number. Okay. So this is a dimensionless quantity. What are the units of heat transfer coefficient? units watt per meter square Kelvin. So remember Newton's law of cooling. The heat transfer rate is H times area times temperature difference. The heat transfer rate unit is watts. So heat transfer coefficient unit is watt per meter square per Kelvin. Okay. So this units here are watt per meter square Kelvin multiplied by meter divided by watt per meter Kelvin. So this is a dimensionless quantity. It's called the Biot number. It's written as BIOT. It's spelled as BIOT. It's called the Biot number. Okay. So we could rewrite this Biot number as L by Ka divided by 1 by Ha. Okay. So all I have done is the cross sectional area at which the heat transport is occurring from the solid to the fluid. I am just multiplying the area in the numerator and denominator, and I have just manipulated the expressions. Okay. What is L by Ka? It's the resistance for conduction. And what is 1 by Ha? Is the resistance for convection, right? So it's important to qualify the resistance for convection, saying that it's the resistance for convection at the boundary. It's the resistance for convection at the boundary of the solid and liquid interface. There is a reason why I am qualifying this. Maybe about 8 to 9 lectures from now, you will see another dimensionless number which looks very similar, except that the definition of the resistance is slightly different. And that's why it's important to qualify it by saying that it's the resistance of convection at the boundary where the heat transport is occurring from solid to the liquid. What happens when Biot number is much larger than 1? Which means that resistance to conduction is much larger than resistance to convection, right, at the boundary. When Biot number is equal to 1, the resistance to conduction is almost equal to, if I say almost equal to 1, convection, and if Biot number is much smaller than 1, then you will have resistance to conduction is much smaller than resistance to convection. Okay. So suddenly, by defining a dimensionless quantity, we are able to use all the intrinsic properties and the dimensions of the system in order to identify when the lumped capacitance method is important. So when conduction resistance is very large, can we use lumped capacitance method? Why? Why can't we use? Right. So when the resistance to conduction is very high, so you should always translate resistances to the temperature profile. Whenever the resistance is very large, you cannot assume uniform temperature. So this means, so when Biot number is larger than 1, uniform temperature assumption is not valid. Okay. So when Biot number is much larger than 1, you cannot assume a uniform temperature inside the system, which means that you cannot use lumped capacitance method. You cannot use the lumped capacitance method to approximate or to characterize the heat transport process. Okay. So now it's almost easy to read what happens when Biot is almost equal to 1. What happens when Bi is almost equal to 1? Can we use lumped capacitance? Yes, no? You can't use, because you still cannot ensure uniform temperature. Keep in mind that the lumped capacitance method works only when you can assume a uniform temperature distribution. So when BO number is almost equal to 1, so note that, so supposing if this is the boundary where you have solid here and the fluid here, so we said that BO number is HL by K, which is dt by dz at z equal to 1 divided by t infinity minus t at z equal to 1. So this essentially signifies the ratio of the temperature gradient at the boundary in the solid and the temperature gradient for convection outside the boundary. So it's not just that it captures a ratio of resistances, it is also equivalent to the ratio of the gradient, temperature gradient inside and temperature gradient outside. Okay. So when these two, resistance to conduction is equal to resistance to convection, which means that there will be significant amount of gradient and these two gradients will be exactly equal to each other. Right. When Bi is equal to 1, it means that the gradient, temperature gradient in the solid at the boundary and the temperature gradient outside the boundary will be equal to each other, which simply means that no uniform temperature can be assumed. You cannot assume uniform temperature inside the solid. So which means you cannot use the lumped capacitance method. No lumped capacitance method is permitted when BO number is almost equal to 1. Okay. So the third case is where BO number is much smaller than 1. Okay. This means that the resistance of conduction is much smaller than resistance to convection. So what does it mean? That the temperature gradients inside the solid is going to be very, very small. So you could neglect. It doesn't mean that there is no temperature gradient. All you can assume is that you can neglect the temperature gradients It's very important to qualify this. When you say neglect, it's actually in comparison with something. So neglect temperature gradient relative to inside the solid relative to gradient outside. So this is the justification for using the lumped capacitance method. It doesn't mean that the temperature gradient is 0, okay. It's an approximation or it's an assumption, and it is valid only when the BO number is much smaller than 1. Okay. So it's the purpose of dimensionless quantities, as you will see in down this course, many dimensionless quantities that will be defined in this course and also many other courses. One of the main purposes is basically to characterize the different ranges of the process, characterize what is going to be the different features of the process at different values of these constants. So instead of looking at the heat transport coefficient, length and the effect of conductivity individually, it is enough to look at the effect or the variations of the features or properties of the temperature with respect to BO number, which actually captures all the effects that is included in heat transfer coefficient, length and the conductivity. So this is the elegance that you get by using a dimensionless quantity and defining a dimensionless quantity. Any questions so far? Okay. Okay, so let's try to sketch the temperature profile. So supposing if BO number is much larger than 1, which means that the resistance for conduction is going to be much larger than the resistance for convection, which means that this means that there will be sharp temperature profile in the solid. Okay. So what I am going to sketch now is the time profile of the temperature distribution in the solid slab. So supposing if I maintain it at same temperature on both sides of the slab, okay, so I will have a symmetric temperature profile. And so supposing if Ti is the initial temperature at which the solid is being exposed to the fluid which is surrounding, and let us say the temperature here is T infinity, then as time passes by, so because the Biot number is much larger than 1 and the resistance to conduction is much larger than the resistance to convection at the boundary, so you would expect that the gradient outside the solid is going to be much smaller than the gradient inside the solid. So as time passes by, so this is T greater than 0, so you will start seeing profiles which will look like this. So you will have sharp gradients inside the solid while you will have not so sharp gradients outside the solid. So this is, we have not solved the equation. Without solving the equations, simply based on the intuitive understanding of how the temperature distribution is going to be based on the Biot number and resistances, we are able to actually sketch the temperature profile. So this is very important. Of course, you will have to write model equations and solve them, but if you don't know how the or what the model equation is going to give, you don't know whether the solution is right. So it's very important to be able to get an approximate temperature profile or sketch of the temperature profile even before solving the equations. And using dimensionless quantities and such resistance arguments, it actually helps you to come up with what is going to be the approximate temperature profile. So similarly, I could draw for Bi much smaller than 1. If Bi is much smaller than 1, what would you expect? It will be, what will be the temperature profile inside the solid? It will be almost flat, it will be almost uniform. So one could sketch the temperature profile. So if Ti is the initial temperature, so you will have sharp gradients outside, but you will have not so sharp gradients inside. Because Biot number is much smaller than 1, the temperature difference for convection outside the solid is expected to be much larger than the gradient of temperature at the inside of the solid near the boundary. And so as time goes by, so you will start seeing temperature profiles which are almost flat inside. Okay. So this is the two different profiles, but Biot number is 1, what will be the profile? It will be somewhere in between these two, right? So this is the profile for one extreme and this is the profile for other extreme condition, and Biot number is equal to 1. You will see a temperature profile where the gradients are not very steep, but at the same time the gradients outside the solid are also not very steep. So they will be equal to each other at the boundary, and so you will see a temperature profile which is somewhere in between these two. Okay. So supposing we next take the actual system, right? We try to sketch the temperature profile in a slab without writing the model equation. So let's now write the model equation. So supposing you have a slab, and this is plus L minus L, and let's say the temperature here is T1, okay, and if the fluid which is flowing around, the temperature is T infinity, okay. So let's write the model, and in fact we can check whether the temperature profiles that we actually intuitively guessed what is going to be the profile, that will actually be the same as what we would predict from the model. So this is equivalent to a half slab, okay, with adiabatic conditions in one boundary, and the temperature here is T1, okay, and we have T infinity is the temperature of the fluid which is flowing past it, and so we can write a model. There will be rho Cp will be equal to note that it's a partial derivative now, and the boundary conditions will be dt by dx at x equal to 0 is 0 and minus k dt by dx at x equal to L. So if I assume that T1 is greater than T infinity, so that will be h into T at x equal to L minus T infinity, okay. So that's the boundary condition, and the initial condition will be T at x comma 0 will be equal to Ti. So the initial temperature of the slab is uniformly equal to the temperature Ti, and one could even assume a certain temperature profile as an initial condition, but let's not worry about that right now, okay. So we can solve this equation. I'm not going to do the math here. It's very similar to the way we did the separation of variables problem in the last lecture. The solution will be, so the solution is, so if I assume theta as T minus T infinity by Ti minus T infinity, and the solution will be summation n equal to 1 to infinity Cn exponential of minus lambda n square into Fo is Fourier number. I'll define in a short while what that is, okay, and Z is x by L. Fourier number is alpha L by alpha T by L square. What is alpha? Thermal diffusivity. So alpha is K by rho Cp, it's the thermal diffusivity, okay, and Cn is given by 4 sine lambda n divided by 2 lambda n plus sine 2 lambda n, and lambda n is the solution of this equation, lambda n tan lambda n equal to BO number. So lambda n are the roots of this equation. How many solutions are there for a given value of Bi? Lambda n tan lambda n equal to Bi. How many solutions? How many solutions? What is the nature of tan? A lot of them. How many? Yeah? It's infinite solutions. So tan is a transcendental function. In fact, the way to see that is, you can actually express it in terms of plot a graph is one way. You can actually see that tan is a ratio of exponentials, right? It's ratio of exponential of imaginary functions, right? So it's ratio of sine and cos. So sine and cos you can write as exponential. So you can immediately see that it's actually infinite number of solutions. So you have infinite roots, and in fact that's why n goes from 1 to infinity here. Okay. How do you solve lambda n tan lambda n equal to Bi for a given value of Bi? Is it linear? It's not linear. So you cannot get analytical solutions for the roots. So you have to use a nonlinear solver. Which nonlinear solver? Scilab. No. Scilab is just a software. Okay. So what you use is called the Newton-Raphson method. You will see this in your numerical analysis course. So you have to use the Newton-Raphson method to solve this equation. And in fact, there are subroutines in Scilab, MATLAB, etc. to do the Newton-Raphson method solution of such kind of algebraic equation.